But because it's going from a vapor to a solid, it's like a formation of a rain droplet. These things are perfectly round and they're smooth, and it's a condensation of that vapor. So you end up with an SiO2 amorphous powder, which is what the silica fume is in that container. This is a shot of what the furnace looks like as they're tapping the silicon metal. Si comes out about 1300, 1400 C. They pour it into big chills. It gets hard. A chill is exactly what it does. It chills the material until it gets hard, and then they drop it on the floor and it shatters like glass, and they start the crushing process. They'll crush it to that size. They'll crush it all the way down to 10 micron for use in some ceramics and glasses and those type things. And what's silicon used for? Silicones. Probably 80% of the market of people that buy that elemental material take it, Dow Corning and GE, and turn it into silicones. Bathtub caulkings you think about automatically, but deodorant, shaving cream, dashboards, cereal boxes, fake Hooters, all those things start out as silicone. That all start out as that metal, that piece of metal that's going around before they turn it into silicones. That's how it all starts. And this is actually the silica fume that goes up the stack. This is a shot of well, that's actually a shot of silica fume particles, magnified, but to show their roundness. Amorphous. Amorphous means non-crystalline, and these obviously are non-crystalline if they're amorphous. The amorphousness, the roundness, is what makes them reactive. You can put crystalline silica in with cement and water, and it doesn't react as a pozzolan. Sand. Sand is crystalline silica. You mix that with concrete and it still stays sand. You mix this stuff with cement, water, in 7 days' time, it's all calcium silicate hydrate. It's no longer silica fume, it's reacted. It's the amorphousness of the silica fume, of the silica particle, which makes it reactive. It's also the amorphous nature which makes it non-hazardous. When people hear silica, the first question we get is, silicosis, it's hazardous. Guys don't want to touch it, don't breathe that stuff, it'll kill you. You got kids. It's not. This is probably the safest thing in a ready-mix plant because it is amorphous. It's considered a nuisance dust. It's respirable. Respirable is in the category of cigarette smoke. You breathe it in, you breathe it out. Crystalline silica, because of its angularity, when you breathe it in, it gets hung up in your aerosols and your lungs and those type things, and that's what produces silicosis. And really laying on a beach on a windy day is probably the worst place to be for, for crystalline silica. A little comparison here, and this is a lot of these shots are out of the user's manual here. The user's manual was put together for practitioners. It's not an engineering document. It's written for ready-mix producers, it's written for contractors, it's written for people that actually have to make this concrete and build stuff out of it. So I think that's this group here, right? Yeah, good. The beginning parts you see in chapter 2 here, we're still talking about what is silica fume and the sizes. We're showing cement grains on the left panel and silica fume or microsilica particles about 100 times finer than cement grains. Cement grains you grind from a rock down to a powder, where the silica fume is a vapor that's condensed. To put it in more layman's terms, we compare it to the Washington Monument. You know, if the cement grain was the size of a Washington Monument, the silica fume particle would only be the size of a 6-foot guy. And we show the crystallinity of the silica of the cement particle versus the amorphous silica fume powder. And again, that shot. Excuse me. What happens in concrete, though? Think about the cement grains. Regardless of how small they are, you can only get them so close together. It's like filling a barrel full of baseballs. You can only get them so close together, and you have that void spaces between all those baseballs. Well, what happens is, in comparing cement grains and silica fume, if we mix baseballs up with BBs, you can see what's going to happen. We're going to fill in all those void spaces between those cement grains, which is really what we're doing with the silica fume. But now we're filling them up with another cementitious material. It's going to react with cement water hydration, so we're going to close off that capillary pore with another cementitious material. So we end up with low permeable concretes that will suck in less deleterious chemicals. Industrial floors, lactic acids, beer plants, slaughterhouses, bridge decks, parking garages. Indianapolis Airport has a 6,000 car parking garage that starts next month. It's all silica fume concrete for this reason, that they want that structure to have a 75-year design life. You get one chance to do it right. You can put as many chemicals as you want on the surface of that concrete and they all wear out over time, or do you do it right the first time and make it low permeable to start with and get your longevity or your lifelongness from that way, that technology. This is probably the first use of silica fume in the United States. The U.S. Corps of Engineers and the Bureau of Rec use silica fume on all of their waterways for abrasion erosion. Water carries aggregates, big rocks that'll tumble and abrade away concrete. And what they found is that by making a very high strength concrete, and they use silica fume to get some pretty high strengths, they're able to make the concrete very abrasive resistance. And can I switch videos here? I've got another one here on this project that I think is coming up next. Yeah. This is this structure is actually on the video that we're going to get ready to play here. This was done back in 1983. A little bit of updated history because the video will tell you everything about the construction. But since it was built, I think, in 66 or 67 and was repaired every 6 years until 83. So it was repaired twice. And this is the result of, they lost a foot of concrete that abraded away, and they actually are in danger of losing their whole stilling basin. So they put 13,000 PSI concrete on here as abrasion erosion resistance, and that was done in 83, and we're now up to 23 years. They used to send divers down every year and inspect it, actually measure the wear and do all those good technical things, and they just said, this is a waste. It's up to 23 years now, we're happy with it, so they don't even go down and look at it anymore, and it's still in place. So they've gotten 4 times the life out of it. Their goal was to get twice the life out of it, and they're up to 4 times as much now. Yeah, go ahead, start up. You can cover that, please.
Technology Company presents the story of MSAC microsilica additives and the concrete used to repair the Kinsu Dam's stilling basin. This ultra-high-strength flowing concrete was used to repair the stilling basin at the Kinsu Dam here in the Allegheny Valley in northern Pennsylvania in October and November 1983.
I'm Mark Luther. I'm a project engineer for Elborg Technology Company. We're working on this project. It's repair of the stilling basin of the Kinsu Dam.
The U.S. Army Corps of Engineers is the federal agency responsible for maintaining the nation's waterways. The Kinsu Dam and its stilling basin is one of its responsibilities. A stilling basin is exactly what its name implies. It stills the water that flows out of a dam before it reaches the main channel of a river or other body of water. If there were no stilling basin, the energy from the high-velocity water would simply gouge out great holes in the riverbed and its banks and possibly endanger the stability of the dam. At Kinsu, the stilling basin is a large area, about 204 feet wide by 180 feet long, with 5-foot thick slabs of concrete. It was originally placed in operation in 1966 and was made of good quality concrete with 6-inch sized aggregates. By 1973, the combination of high-velocity water flow and the presence of debris in the basin had eroded the concrete surface and caused general erosion, with holes as much as 3 feet deep. That same year, the U.S. Army Corps of Engineers let a contract to repair the entire slab with a 1-foot minimum overlay of low-slump steel fiber reinforced concrete, the very best concrete then known for this type of repair work. 9 years later, in 1982, underwater inspections by divers showed that in some places, the 1-foot overlay of steel fiber reinforced concrete had been worn away, and as much as 2 feet of the original slab was also gone.